Hello, I'm Dr. Thomas Howarth, a Royal Society Dorothy Hodgkin Fellow and lecturer at Queen Mary University of London. And here I want to talk about some work that I've done recently looking at Proplyds in NGC 2024, which is also known as the Flame Nebula. So first of all, what is a Proplyd? Well, back in the mid-90s, we got our first direct view of disks around young stars, and this was achieved by observing them in silhouette against the bright background of star-forming regions, and the term Proplyd just meant protoplanetary disk. And so any disk, regardless of whether or not it was relatively flat or otherwise, as we're showing here, was referred to as a proplyd. So these disks are strongly irradiated ones, and you can see that they stop looking like the kind of disk you'd normally think of. They end up cometary in shape. So they're heated up and plumes of material come off of them, and so you get a bright cometary cusp and then a tail behind them. And these point towards whatever source is responsible for irradiating them. And so the term proplyd has evolved over recent years, in particular, to now be referring to these kind of systems rather than just any disk. So a proplyd is a strongly irradiated disk that doesn't really look like a disk anymore. It's got this classic cometary shape. And where is NGC 2024, where I'm looking for these? Well, it's in the Orion constellation. Here we have the three stars of Orion's belt, the Horsehead Nebula. The Orion Nebula is down here, and this here is the Flame Nebula NGC 2024. Let's just zoom in on it. You can see there's some foreground material here and a bunch of star formation happening in the background. And this is the youngest star forming region in Orion, and we'll quantify that in just a second. So earlier this year in 2020, Van Terwizga et al. Looked at the central part of NGC 2024 in an ALMA millimeter continuum survey. And what they found was really interesting. So here is a map from their paper. You have Herschel contours here. So there's a dense star-forming cloud there. And this diagonal line distinguishes two populations that they discovered. So you've got an eastern group and a western group. And the western population is about 1 million years old, and about 15% of the disks in that region were observed in the millimeter continuum. So they looked at a whole bunch of stars, and only 15% were detected in the millimeter continuum. So it's very depleted in large dust grains potentially. In the eastern region, it's similar age but slightly younger, at about 0.2 to 0.5 million years old, and there the millimeter continuum disk fraction was about 45%. So about half the disks have millimeter dust over here, and only about 15% over here. And the interpretation proposed was that you have two relatively massive stars in the region, so a B0.5 and an O8 star, and they were thought to be working in tandem to have evaporated this only marginally older population. So there's some clear line of sight here for the O8 star to evaporate the disks over here, and in this side the disks are just relatively well protected because you've got this star forming material. So this prompted me to go and look for signs of evaporation in the region. This is very important to understand if it is happening here because it's so young. If you look at HL Tau, it's only about 1 million years old, or possibly even less, and has signposts of planet formation. So, would it have been able to do that if it were in this kind of hostile environment? And I looked in archival data. This is actually from 2003, just from Hubble, and found 8 proplyds. So this is again a map of the region with the diagonal line distinguishing this marginally older, very millimeter continuum depleted population and the younger population where the millimeter continuum disk fraction was about a half. And so there's 8 proplyds discovered in this archival data. So they're 1, 2, 3, 4, 5, 6, 7, and 8. So we're finding proplyds in both regions. And let's just take a quick look at what they look like. So proplyd 1 is over here near the B0.5 star, B0.5. And this proplyd 2 is also near this B0.5 star, and they're both pointing towards that. And we'll talk about that and the implications in a second. Proplyd 3 is a sort of classical, beautiful cometary morphology and is pointing towards this O8 star, O8 star, IRS2b. And proplyd 4 is possibly a binary proplyd, again pointing toward IRS2b. From here on in, you have to sort of squint at these candidate proplyds. So this is candidate 5, 6, and 7. So they're all pointing towards IRS2b over here. and the final one is candidate 8, which is right up off here and is pointed towards IRS1. So this is just a quick gallery of the proplyds that we think we've discovered. So what are some of the implications of this? Well, one that I've already alluded to is that the B0.5 star IRS1, it looks like it's responsible for causing the evaporation in this depleted region on its own. You don't really need IRS2b to help. So the reason I say that is that the proplyds, as I already mentioned, point accusingly towards whatever source is irradiating them. So here is proplyd 1 pointing at IRS1, the B star, and here is proplyd 2, it's around here somewhere, again pointing at IRS1. The O8 star is right away off of this side of the image, quite a long way away, and there's no indication that the heating here is being directed towards that star. It's definitely both towards IRS1. So this is actually important to mention just because we shouldn't just ignore B stars as being possible sources of strong evaporation of disks. Normally we just focus on the O stars, but B stars seem very capable of doing this too. You can also measure the mass loss rate from proplyds if you can measure the size of the ionization front. So you recall there's this bright cusp and then a tail. If you measure the size of that cusp, we can theoretically relate that to the rate at which material is lost from the disk. So the theory says that for a given size of cusp at some distance from a source of known UV properties, you can have these regions of constant mass loss rate. So this is a mass loss rate of 10 to the minus 9, 10 to the minus 8, 10 to the minus 7, 10 to the minus 6. And the reason we have a shaded area is just due to uncertainties on the stellar temperature and radius. So uncertainties in the UV properties of the ionizing star. And then the points here are the measured distances, so projected distances from the B star, and the measured cusp sizes for the proplyds, and that gives you mass loss rate estimates. So proplyd 1 and 2 have mass loss rates bigger than 10 to the minus 7 solar masses per year, and candidate proplyd 8 has something more like 10 to the minus 8 solar masses per year. And then in the younger eastern population, all of the proplyds seem to have a mass loss rate bigger than 10 to the minus 7 solar masses per year. So the mass loss rates are very significant. Another thing we have from the Van Terwilliger data is estimates of the masses of these disks in the millimeter continuum. Now, I know there's complexities associated with turning that into a total disk mass, but just to take a quick stab at what we expect the lifetime of these proplyds to be, you can do basically just the ratio of the mass to the mass loss rate, and that will give you a time scale. Now, there's other uncertainties beyond just what the actual mass of the disk is. The way evaporation operates is that the disk shrinks and then stalls. The external photoevaporation isn't as effective when the disk gets very small and is very tightly bound to the star. So the disk will persevere longer than the system will be a proplyd for. So there's lots of uncertainties here, but you can just take a rough stab at it and make this kind of estimate. And if we do that, we find that the proplyd lifetimes in this region are only about 0.1 million years at a maximum. So this is really short, and it gives rise to something that's well known called the proplyd lifetime problem, and it is seen in other star forming regions, and how you resolve this is still not fully understood, but you could have ongoing star formation, you could have that the disks are maybe more massive than we expect, or you could have that the proplyds are systems that have just recently migrated in towards the massive star. And we'll come back to this in a second as well. Another thing we did was look at whether or not there was any statistical imprint of the environment on the disk properties. So in places like Sigma Ori, we've been able to see trends in the properties of the disks as you get further away from the massive stars. So if the disk masses, for example, get larger as you get further away from an ionizing source, and that's potentially evidence that the ionizing source has been depleting the inner disks of material, the disks that are closer to it. And we don't see anything like that here, but that's not very surprising. In the depleted Western population, most of the disks just are depleted. We don't really see anything. And the proplyds in this plot here of mass as a function of projected distance from the B star, the blue points are just the proplyds. So we have mass estimates, and you can see they're just some of the more massive systems there. So that's maybe why they've persevered longer than everything else. And then in the the younger region, everything's just a bit of a mess. It's a star-forming cloud. It's very young, so you don't really again expect to see much of a statistical imprint just yet. It's also worth noting that at this kind of scales we're looking at here, so 0.2, 0.3 parsecs, the time for the cluster to relax is very short. So even if you did imprint a signature at such small scales, it would quickly wash out just due to the dynamical evolution of the stellar cluster. Final implication. So I mentioned that in the depleted side, we think the B star, it can be responsible for the evaporation on its own. What's going on in the other region? Well, I believe that IRS-2b is essentially just stripping away this star-forming cloud sequentially. It's evaporating it. And as it's doing that, it's unveiling these young stars with their disks and then quickly destroying the disks. So this gives you another way of solving this Propylid lifetime problem, is that these actually really don't live very long, but there are a lot of sources embedded in here. So the cloud gets stripped, the disk gets exposed and evaporated, and then you unveil the next generation of stars that will start being evaporated as Proplyds. And there has actually been fairly widespread evaporation of disks here. The millimeter continuum disk fraction is about 45%, but this region is only about 500,000 years old. If you look at lupus, the millimeter continuum disk fraction is more like 70%, and that's about 1 to 2 million years old. So this region has been quite severely depleted, and I'll reiterate that this could be really important for planet formation, given it's being seen to happen early. This is definitely on a competing timescale to planet formation. So look out for the paper. It should be out on the archive very soon, if not already by the time of this meeting. And I'm happy to discuss it here and via email as well if you want to get in touch offline.